Hi, in this video we will learn about the squeeze theorem. It's a theorem which will be very useful while trying to find a little bit complicated limits. The squeeze theorem is a simple incarnation of a fact which in wording I can say it in this form. Limit respects inequality. A little bit vague, but what it says is, what I mean by this fact is that, well, this is the mathematical fact, and in your book actually it is written as a theorem. It says that, well, if we have two functions, f of x and g of x, such that f is less than equal to g for some values of x, well, values of x around a, so for x around a, and since we are going to work with limit, we don't care about what happens at a, so except at a. And we know that the function f and g have limits, so and functions have limit as x approaches to a. So if a function is less than the other one, so it's like if you have a function here, this is g, another function f. If these functions are one is less than the other one, the limit at any point that you have this inequality around, limit of the lower function is going to be less than limit of the upper function. In other words, here in writing it says that limit of f of x as x approaches to a is going to be less than limit of g of x as x approaches to a. Very nice. This is the way I said. It's just limit respects inequality. Yes. This can have very nice implications. For example, there is no value of a such that limit of 1 over x squared can be equal to 2 as x approaches to that a. There's no such a. Why? Well, you see, x, you start with any number in real numbers, then square it. That's going to be a positive number, yes. And then you add 1, that's going to be bigger than 1. Now, this is the denominator of the function. You can find its inverse. If a number is bigger than 1, you inverse it, you will get a number less than 1. And, well, now you have two functions. This function is our f, this is our g. As a result of this thing, as a result of the fact we just had up there, limit of 1 over x squared plus 1 as x approaches to a, for all a that limit exists, just use the basic facts we know about the limit laws. This is going to be less than limit of the constant function a, 1 as x approaches to a. Well, limit of constant function 1 is always 1, and that means that limit of our function, no matter what you choose for a, is going to be always less than equal to 1. And that's why it cannot be equal to 2. Very nice. This is very simple application, but a little bit elaborate application of that will give us what we call the squeeze theorem. In the squeeze theorem, you have three functions. Let f of x be less than g of x less than h of x for x is around near a, but again except at a. So you can always exclude a, the point at because we are going to find a limit as x approaches to a. Then if limit of the lower function as x approaches to a is exists and equal to limit of the upper function as x approaches to a, and these are same numbers, then you can conclude that limit of the middle function as x approaches to a exists and it's equal to L. And well, what it says here is that, okay, now you have three functions, f, g, and what we have is that f is less than g around that point a, and f and h, sorry, let me just put h here, and then there is another function g which lives between these two around that point a. This is g. Then as x approaches to a, these two functions, upper and lower function, will squeeze g into the same exact limit. That's what it means. You may say, well, how come, well, we have two limits, how this can be useful for us? We have to compute two limits to conclude what is that one limit, middle one. Well, it can be useful because the limit of here, the upper and lower functions can be very easy to compute comparing to the limit of the middle function. For example, indeed, we can have cases where we don't have any other information about the middle one, but satisfying an equation, so an inequality. So f g is a function which satisfies the following inequality for all x's. Okay, let me just write it. G of x is less than x cubed minus 6x squared plus 12x minus 5, and g of x is bigger than that and less than x squared minus 4x plus 7 for all x's near 2. Then find limit of g of x as x approaches to 2. We don't know anything else about g, but that it satisfies this equation. Upper and lower, the function which is greater than g is a polynomial. The one that is less than is a polynomial. Finding their limit as x approaches to 2 is nothing but a direct substitution. So we only have 2 cubed minus 6 times 2 squared plus 12 times 2 minus 5. And that gives us what? These two cancel each other. 8 minus 5, this is 3. A limit of the function which is greater than g as x approaches to 2 is 2 squared minus 4 times 2 plus 7. And, well, that's negative 8 plus 7 is negative 1. This is 4 minus 1. This is 3. These two have the same limit, so they will squeeze the middle one as a theorem of Squeeze theorem, as a result of a Squeeze theorem. these will squeeze the middle function, which we don't have any other information about it, as x approaches to 2 is going to be equal to number 3. Or sometimes even we can do everything from the beginning and find the inequality and the limits and evaluate the limit itself. For example, let's find limit of x squared times sine 1 over x as x approaches 0 if it exists. Yes. Well, first thing you see that, okay, so this is product of two functions. I know limit of x squared as x approaches to 0 is 0. If I can find what is limit of sine 1 over x as x approaches to 0, then I can use product law and then multiply the limits. Done. That should be easy. Well, but it won't work here for a very nice simple reason. Sine 1 over x, if you sketch it, you'll notice that it goes, it's a function like this, gets closer to 0. The closer it gets, the crazier the function becomes. It just goes up and down, up and down, up and down, up and down. At 0, it's not defined, but it oscillates as we get closer to 0. And the same thing goes the other way around, like up, down, and then as we get closer, it just does crazy things. So the limit for this guy actually does not exist. Since the limit does not exist for one of the factors, we cannot use product law. Okay, so done. That simple idea cannot work here. But instead of that, we can see that, well, sine of anything you give me, this is a number between 1 and -1, isn't it? This is the way sine is defined. Well, in particular, we can have sine of 1 over x there. Well, okay, we have to be careful. I cannot plug in x equal to 0 because it's 1 over x. Yes, that's all right. It doesn't change anything for us because we are going to find the limit as x approaches to 0. But this is not our function. The function we have is multiplied by x squared. Well, then multiply both sides by x squared. X squared is a positive number, and then we can multiply. So it will be negative x squared sine of 1 over x and less than x squared. Very nice. Now we have an inequality where has our function as a middle one. There is another function less than that, another function greater than that. And this inequality again is true for all x's between for all real numbers but x equal to 0. Okay, so then we need to check what is the limit of the lower one as x approaches to 0. Well, this is just simple substitution. X squared as x approaches to 0, 0 squared, this is 0. Now, this inequality, this limit, and this limit, all three are the assumptions of the squeeze theorem. So we can now use the squeeze theorem and conclude that the limit of the middle one exists and it is equal to what we found there, 0. And if you want to look at this graph of x squared sine of 1 over x, you'll notice that this has a funny graph, which is, well, this function is going to be between two parabolas. Yeah, so this is the upper parabola x squared, so I'm drawing a little bit, and then this is lower parabola. This is minus x squared, this is x squared. Then the function sine 1 over x again starts somewhere like that, then goes up, goes down, up, down, bouncing back and getting crazier. But at 0, it's not defined. And then same story for the negative parts, and so on. What happens at 0, these two x squared and minus x squared squeeze this function to limit 0 as they have. So limit of x squared sine of 1 over x is going to be equal to 0. This is one of the limits that we cannot compute that easily without this squeeze theorem.